Hey everybody, welcome back. My name is Andy, and today we're going to continue working on our Python 3 NES emulator. So just to give you a bit of background on what we're going to do today and what we've been doing. So basically we started yesterday doing a Python 3 NES emulator from scratch. There is a VOD up of the first episode where we kind of went through some of the basics and tried to walk through what was required to create this emulator and then what we're going to focus on. Since then, I've gone through and updated the repo, which has given us... Ooh, getting some feedback there. Let me just mute that. I've gone through and updated the repo, which has given us some useful links now and links back to the stream and to the recordings. So episode 1 is up and going. Cool. Alright, so what did we do yesterday? So the point that we got up to yesterday was... Well, let's start from the beginning. What are we trying to do here? We're trying to emulate a NES. And so the way that we're going to do that is by simulating all the different bits of the hardware. So that's going to be all the CPU and the PPU, which is essentially the graphics card, as well as, the memory and anything else that we're going to need. So yesterday we created a Python program. This is going to be all done using Python 3. I'm trying to focus on some of the new properties of Python 3. So that reads in a ROM path, creates a ROM, which is a class we made, which looks at the header and pulls the program bytes out of it and can basically return some bytes from a given position. And then we've created a CPU, which is going to basically set up some registers, which we haven't done yet. It's got a program counter to iterate through the ROM memory. And it's going to load in a set of instructions that it can understand, which are a set of assembly instructions. And it's going to turn them into a map. So later, when we're running the program, we can iterate through the ROM and turn it into instructions that the CPU can understand and can execute. Cool. So what are our instructions we've implemented at the moment? So we've implemented a base instruction, which is just going to be an abstract thing that's got some properties, but we've implemented an LDA instruction, SEI, and CLD. So what are these? So these are types of instruction for the 6502 assembly language, which is what the chip on the NES is going to use. Cool. So SEI, LDA, CLD. So at the moment they don't actually do anything. They don't execute beyond printing out their string. So we kind of have something that can go through, it can recognize instructions, but at the moment the instructions don't do anything. So again, to come back to the ROM, this is what the ROM is going to look like. These are all the bytes, well, this is all the hex, but this is all the bytes. Every 2 hex characters represents 1 byte. And the program code starts here and continues down. So this first one is an SEI instruction, 7-8, and then D8 represents a CLD. A910 represents a LDA instruction. So what are we going to do today? Basically, we're going to start implementing what some of these instructions actually do, and we're going to start properly implementing a CPU. So have it be able to maintain registers, have it be able to maintain memory, and ideally have it start to be able to understand several of these instructions. Cool. Alright, so let me just do some stuff on this monitor. Cool. Alright, let's get started. So to do that, we're going to go back to our Wikipedia article on the NES, and we're going to read some of the stuff. So I've linked that down to here, some of these useful links. In particular, this one, we're going to look at the 6502 Wikipedia page and the NES Dev Wiki, and we're going to try and pull some information out of them. So the 6502 is the CPU that we're emulating, and if we look at the instruction set, we can see that these are all the instructions that we're going to have to implement. So there's 155, I think, implemented ones. There are 256 possibles, because it's a 8-bit system, but only 155 been implemented. So we are currently looking at this one, LDA, CLD, and SCI. So we need to figure out what these actually do. And the answer is, I have no idea. So let's follow some references and find out. 6502 instruction set and 6502 opcodes. Perfect. So this is probably something that's going to take up this episode, and probably a couple more is going to be implementing some of these instructions. So yeah, let's settle back and see what happens. Let's start with the SEI instruction, because I believe that is our first instruction. Alright, so that's going to set interrupt disable. Right, so already we're kind of hitting a wall. So what this is telling us is that we're going to need to looking at the flags. So the CPU doesn't only store, in a second, I might just sketch this up. So the CPU is going to sit over here, and it's going to talk to all the other components, but it's also going to communicate with the PPU and the memory and stuff like that, but it's going to maintain its own internal state. And so how does it do that? So we kind of went through this a bit yesterday, but I'll just rehash it a bit. It maintains this is in the 6502 CPU, at least. It's going to maintain 3 registers, X, Y, and A. So these are registers. And what are registers? Registers are just a really fastly accessible way of storing a single byte of data. They're probably physically stored with the CPU, I presume, but to be honest, I'm not 100% sure. Alright, cool. So what else is it going to store? It's also going to store a set of flags. Now, what are these flags? I don't know. Let's find out. I just know that they exist. So this NES wiki is a very useful thing for creating NES emulators, or writing NES ROMs if you're that way inclined. So we're going to go to the CPU. Cool, so CPU instructions, addressing modes, we don't really care about, I think you can see them all here. We don't really care about the instructions at the moment, although that's what we're going to be implementing. There's just going to be links out. We can come back to that later. What I really want to be looking at is registers, because they're going to be useful for us. Power up state we're going to have to do eventually. We should probably do now. And status flag behavior. Cool. So status flags is what we're going to want. Memory map, we're going to have to do this later. What's the PPU? Is that specific to the NES? The PPU is a picture processing unit, in that it is a graphics card, essentially. So it will handle all the graphics, so blending things to the screens and managing sprites in memory and stuff like that. Eventually, obviously, that kind of got renamed to a graphics card, or, was the precursor to what we consider a graphics card today. There is also an APU, which is the audio processing unit. So I might just do this over here. So PPU is going to manage our sprites and our drawing, and our APU is going to manage our audio. Yeah, I believe that name is specific to the NES, but it's a pretty generic term, I suppose. Yeah, we can see the APU and the PPU here, and then the rest of it's ROM or RAM. Pins out, signals. I don't think we need to bother about these. These are hardware things. Maybe. Yeah, so these are our status flags. So our status flags are stored in a single byte called the flags register. Right, so it actually is a register, which is going to sit down here, and it's a single byte, and it's going to be called our F register. No problem, happy Benz. Yeah, feel free to chuck any questions. I'm happy to at least try to answer them. I can't guarantee that I'll be good at them, but yeah, so the flags register, also called the processor status, or just P, okay, is one of the 6 architectural registers. Huh. Cool. So there are 6. I only know about 3, and I just learned about a 4th. So I'm guessing we're going to find out about 2 more at some point. But that's fine. Alright, instructions modify 1 or more bits and leave others unchanged. Right, so it's going to do this by doing bitwise ORs, presumably. Or bitwise ANDs. Bitwise operations. Instructions that save or restore the flags map them to bits in the architectural P register is shown below. Right, so I believe the way that it works is that, so the first 0 or 1 is going to tell us if a carry operation was performed. The second 0 or 1 is going to tell us if the operation resulted in a 0 value. So I believe that this is for a branch operation, so you know when to branch. Do I have a computer science degree? Yes, I do. So I have done a little bit of MIP stuff before, which is another assembly language, and I've done some CPU simulation before. I've never done any emulator work, but I have done a tiny bit of something in the field, basically. Interrupt, inhibit, 0 IRQ. Right, we probably don't care about interrupts for now. We probably will eventually. Decimal, make ADC, so that's going to be your analog to digital converter. And your SBC, I don't know. Ignored on second source 6. Okay, cool. Right, so binary coded decimal arithmetic is something that is in the 6502 in general, but was actually taken out for the NES. So basically, we don't have to care about this 4th bit. We don't have to care about bit 5 and 6 because they have no effect. This is our overflow bit. If there was any overflow, as opposed to a carry. I don't know what the distinction between that is. What's a carry? Last addition or shift resulted in a carry. Cool. Negative, set bit 7 of the last operation. Set bit 7. Yeah, so if it's a negative number, so presumably we have signed numbers, and this is going to be set to bit 7, which is going to tell us whether it's signed or not. I've always found assembly languages really hard to understand. Yeah, so do I. I think this assembly language, 6502, seems like a really nice one. There are only 150 instructions, and of these, there's a large chunk of repetition. So if you could look here, you can see the LDA, which is going to be load into the A register. So load a value into a certain register. Exists here, 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 here. You know, there's like 6 of them. And the reason that there's 6 of them is that they all have different modes of addressing. So you can say, hey, grab the value, you know, put this value in, a specific value, or grab a value from memory, or grab a value from memory with this offset, so on and so forth. So I think, and those addressing modes are consistent between all these things. So I think there's actually not going to be that many unique operations to implement for this CPU. Maybe 100, less than that, 80, 50. I could count, but who knows. So it should make it a bit simpler. And they're all pretty simple operations. Cool. What now? Let's set some bits. And I believe if we look at the status flag. Cool. CPU registers. Here we go. Here's our CPU registers. The accumulator, which is our A register. 2 indexes, which are X and Y. a program counter. So the program counter is a register. Right, cool. So the program counter is going to be what we use to measure where we are executing our code from. So basically you point the program counter to the start of the code that you want to run, and then you let it be incremented as it runs through the different instructions there. And then basically the CPU will just check the PC of whatever value that is, and it'll go and grab the code that it is at that location and try and execute it. A stack pointer and a status register. So P, this is our status register. And then lastly, we're going to have a stack pointer. So what's a stack pointer? So a stack pointer is going to be where we store our variables for a function, for example. So it kind of gives you a local scope. So the idea is if you called a function, your stack pointer would be moved to the top of the stack or the bottom of the stack, if it's growing or coming down. Anyway, it'll be moved to the top of the stack, and then as you add variables on top of that, we'll be able to see that those things are all in our function's namespace. And then if we ever want to go back, so like return from the function, you can just delete anything that's above the stack pointer without, because you know it's going out of scope. That's probably something we'll have to deal with at a bit of a later point. I'm not too worried about that now. Cool. Power up state. So this is going to give us the power up state for all our registers, which is going to be really good because now we can start emulating what our registers actually are. Cool. So if I'm going to move this over here, I'm going to move this over here, and then I'm going to start implementing some of our registers to do proper registers precisely. All right. Sorry, just give me a second over here. Cool. All right. So instead of registers being a list, really what we want is to store each of these registers separately because we know there are only going to be 6 of them. Let me just move this over a bit. So what do we have? We have our PC reg, which we're actually already storing, but I'm going to do it up here as well and delete the old one. So what can registers do? Store a single byte. We're going to set them to none at the start, and then we'll have a function that runs the setup, the boot up parameters. So essentially, we'll try booting the registers, which is just going to simplify this constructor code a bit. All right, so we have a PC. We have a stack pointer reg. We have our preg, which is actually our, so I might just annotate these, program counter, stack pointer. This is, what is this called? Status register. And I have to conform to Pepe. What else have we got? We've got our 3 more. We've got our X, our Y, and our A. So these registers are more our CPU registers. So they're used by the CPU to store status and stuff like this. So call them our status registers, even though this is called the status register, but whatever. And then we'll also add in our data registers, is what I'm going to call them, which is going to be our X, our Y, and our A. And so this is where we actually store data if we want to do operations with the CPU. So a lot of the CPU operations will be like load data to X, or pull data out of X, or add X and Y together and store it in A, so on and so forth. So self.xreg. Let's be dodgy and copy and paste, because that has never gone wrong ever. We've got an A reg. Cool. Alright. I need to remember to update the comments. And they also store a single byte. Right, okay. Now we stored our program counter down here before. We're actually going to get rid of that and instead use the program register, PC reg. So we'll just get rid of that and we'll say, now interestingly enough, this is going to be interesting because we need to figure out whether we actually set this in our initialization state or whether this gets set by the ROM. But, well, one way to find out, I suppose. Where is our power up state? So this is what's going to happen when the NES turns on. From a US NTSC NES, that's fine. Manufactured. The values are probably slightly different. Okay. Please note you should not rely on the state of any registers, and especially not the stack register and RAM. Okay. Cool. Alright, at startup, so PQ equals 34. So what is this 34? This is a hexadecimal value. And if we convert this into binary, this will tell us what our flags are going to be. So I'm just going to start this program, mainly so I can come down here, which I believe is probably going to be covered by my webcam now that I think about it. Oh well. So what do we want to do? We want to turn 34 into decimal. So I know how to do that in this console. We could also do that online, but you know, whatever. From hex 34. Yeah. And then I want to cast that to binary. Binary? Bin. Nope. Are they the same as data regs? I believe that all the registers are the same. They all just store a single byte, but they are, you're correct, they're just used for different purposes. That could be wrong. They could be implemented differently, but I think as far as we're going to implement them, they're just going to store a single byte. Alright, instead 34 in hex to binary. So Google's typically pretty good at doing these kind of conversions, I hope. Nope. Alright, 34, convert. So if we look at the power up state of the P register, it's going to be 34, IRQ disabled, which is, IRQ is interrupt request something. I'll probably have to look that up. IRQ are hardware lines over which devices can send interrupt signals. Cool. When you add a new device, sometimes you need to set its IRQ number. Alright. Figure out what that means later. So we've got a binary value now of what this hexadecimal value means. And it's 0, 1, 0, 0, you know, yada, yada, yada. So let's copy that and let's take that to here. And we're going to make a def startup CPU method. And what's the startup going to do? It's going to set the initial values of all our registers. A status register is intended to store flags. Great point. This, I might, yeah, okay. Status registers. So this P register, I'm actually just going to call this the status register so I know what it is. The status register stores flags. These are actually not status registers. These are something like counter registers. And what these are intended to do is going to be tell us where the execution of the program is, or where the current location of the function is in data, essentially. So yeah, this status reg is actually separate to these two things, which is separate to these, but they're all implemented the same way, I think. All right, startup, cool. So we want to set the initial values of the CPU registers. So status is going to be set to 011000. So what does 001000 convert to? So if I look up the registers, here we go. So we've got this diagram, which is going to tell us it's negative overflow, nothing, nothing, decimal, interrupt, 0, carry. Yeah, thanks, Happy Pants. So if I copy that in here, I'm going to paste this in here. So we could ignore these two S's, so we can get rid of these two ones. And so we're left with MVDIZC, and they're all set to 1 with the exception of I. So what's I? Interrupt, presumably. Interrupt inhibit. Right, so it means that we can't send IRQ signals at the moment. Only NMI gets through. Who knows what NMI is, but NMI. Non-maskable interrupt. Whew. Cool. Alright. Interrupts are going to have to be something that we handle later, I think. Maybe. Alright, whatever. So the point is that we can't send IRQs. I do believe, I did see here though that the IRQ was first asserted around 1/60th of a second after the power up by the APU. Right, so this is probably why we do this, so we don't get hit by this IRQ, I presume. Yeah. And then later on we can turn on the IRQ so that we can then get future interrupts. Alright, A, X, Y all equal to 0. Cool. And what does this mean? It means interrupts IRQ is disabled. X, Y, A are all going to be equal to 0. Your stack pointer is going to be equal to FD in binary. What is FD in binary? Oh, actually, we don't even need to convert this to binary. FD is just going to be an address. So, set to some address in memory. 4017. Okay. Equals 0. Right, so I think if I look at the memory structure of what the CPU is going to look like, God, which is going to be here. So this is an 8-bit CPU, meaning that it's 8-bit, 1 byte, meaning that it can only read in a single byte, or read in, whatever. It looks at a single byte at a time. It indexes things byte-wise. It does, however, have a 16-address memory bus. And what that means is that instead of only being able to access 0 to 256 bytes, which probably is not very much, it can access 0 to 65,138 or whatever it is bytes. So what this means is that, and the actual NES only has 2 kilobytes of RAM. So what this means is that only the very start of our RAM is taken up by this 2 kilobytes of RAM, and we still have, 50 kilobytes or whatever left of space that we can address. So mirrors of here to here. So basically it looks like we mirror all the RAM, presumably for making maths and stuff easier. I don't know why we do that. But what we're saying is that these are all the same thing. So if you addressed 1-800 in here, it's probably going to be the same as 000 here. Maybe. I guess that's what mirroring means. Name table mirroring. Oh. Memory mirroring. Yeah, with the same byte being accessible at more than one address. Ah, right. Yeah, so it just simplifies this because it means we probably don't need to calculate this MSB, for instance, because it's all going to be the same. That's a pretty cool trick. We probably don't need to worry about that though. 2000 is the PPU registers, mirrors of this, again, just to make things easier. APU and IO registers, we probably don't care. Oh, IO registers. Actually, we do care about them. That's what it's going to be talking about. Cartridge space. So this is where the bulk of the memory is going to come, is in this, putting in the cartridge. So this is how you talk to the cartridge, is you just address a value that's above 4020. Alright. Yeah, now at the very end here, f of A, f of B, you have these vectors, which looks to be, instead of putting these in separate registers, they've just put them at fixed locations in memory, presumably just to save on registers. So we'll just need to remember those memory locations and make them store signals. We can do that. So just to check, 4017 is going to be this IO register, right? Register map, cool. In addition to the registers, it contains 22 memory map registers for doing different things. Unlike the addresses of the PPU registers, they're completely decoded. Right, so we know where they are and they're just in memory, and that's how we use them as registers. Oh boy. Square. So we probably don't care about any of these sound ones. So when I come back to here, 4017 is going to be joystick data and frame counter control. Cool. Anyway, so for the moment, let's say that we set memory location to 0, and we kind of at least know vaguely what's going on now, is that these are just going to be separate registers, which tells us that the frame IRQ is disabled, so we can't send frame interrupts. Are the F indicative of anything, i.e. 3FF is any number in the 3000? No. So the Fs are, what this is, all these numbers are written in hexadecimal. So, which is also called base 16. So basically, just give like a super quick overview of what that means. All it's trying to say is you could write the number, if you wanted to count up in, I won't go through what hexadecimal is fully, but if you're counting up in hexadecimal, you go 0, 1, 2, 3, 4, 5, 7, 8, 9, and then instead of writing 10, like you would in binary, which has 2 digits, you can continue all the way up to 16 in hexadecimal. So the character A means 10, 11 is B, C, so on and so forth. D, E, F. F represents the number 15. So when they're writing 400F, what they mean is this number in hexadecimal, which is actually going to be something like, I don't know, 7,000 or something in binary. So in what we would consider a number. So it's just a different number system. If that doesn't make sense, Happy Bands, I did go into that in a bit more detail in the previous episode that I did, which there's a recording of, but it's, yeah, that's something that's going to come up a lot. 4015. Cool, all channels disabled. I have no idea what that means. Let's look at the status flags. 4015, sound chain. Alright, sound channels enabled. We probably don't care about them, but let's do it anyway. So I'm just going to put these in and leave them as comments. That makes sense. Sweet. That's awesome. Yeah, like I said, I did go into a bit more detail in the previous video. If you do want a better overview. 4017. So this is going to be set to 0 and this is going to be set to 0. So what does this do? Frame IRQ disabled. We don't know what that means at the moment, but can't hurt to put it in. So when we do know what it means, we know where to look for it. Alright, frame channels disabled. 4000 to 4000F equals 0. Not sure about 410 to 413. Oh well, we'll just set them all to 0. So what are these? 4000 to 4000F. 4000 to 4000F. So all of these. Unsure about these. Unused volume, triangle. Yeah, so these look like all like sound things. So this is what we're going to have to more worry about when we're implementing the APU. But that is definitely not going to be anytime soon. So we'll call these sound registers. And really we're setting the stack pointer to this. We're setting the regs to that, and we're setting the status reg to that. Cool, so let's do that. So the status reg gets set to bytes.fromBinary, decode. Alright, I need to look up how to turn binary Python hex to binary. ASCII, that seems pretty cool. This could also be called bytes to ASCII. Bytes to bits. Oh god, no way. I don't really want to do that. Bin. So we can call bin on it. Nah. Operations are much faster when you work at the integer level. Interesting. In particular, converting to a string as suggested here is really slow. If you only want bit 7 and 8, we're going to do some bit shifting. Right. Yeah, okay. God, bit shifting. Rock on. Alright, so we're not going to do that at the moment. But eventually we will have to do some bit shifting stuff to be able to access some of these binary things. Which is not too bad actually, to be honest. Alright, power up state is actually set to 3.4, so I might just do it that way. And say the hex value of this thing is going to be 34. Cool. Self.x is going to equal so we want to store this as a interesting. So the xreg can actually only store a single byte, which means it can store any value from 0 to 256. Yeah, so at the moment we're going to store it as a bytes. Because Python doesn't have a byte operator. It does have a bytes, which we're going to use right now, and just have a single bytes to represent a byte. But yeah, I'm unsure whether that's going to be the way to do it in the long run. the answer may well be just store it as an int instead of a bytes. In fact, I think I'm gonna do that, maybe. We'll leave it as bytes for now, and we'll see what happens. I might just leave it to do, because I'm unsure if that's going to actually come back to bite us. Alright, so X, Y, and A. So A is actually a bit special compared to X and Y. These are just going to be value storing regs, and I believe that A is the accumulator reg. So whenever you're doing addition or multiplication or whatever, or something like that, some kind of operation, the result is going to end up in this A reg, I believe. So if you do like regx plus regy, it's going to end up in the A reg. Alright, status reg. Let's set the stack pointer. What do I call that? What's the stack pointer called? SP reg. Sure. Equals FD. So this is definitely going to be stored in bytes. Basically, anything we want to store anything in hex, we probably want to do. Whereas I think these ones we're going to change to int because we probably don't want to store them in hex. Alright, these memory things I'm not going to do for now because we haven't implemented our memory. Implement. Cool. Alright, what's next? We've now got some things. We've now got an initial state. Our PC, is our PC set by this operation? No, it's not. Yeah, okay. Cool, so what that means is that I'm going to continue setting it to the start of the cartridge ROM. The start of the cartridge PRG, so the cartridge code, until something tells me otherwise. Yeah, cool. Alright. Let's do that then. So the PC reg is now going to store a value of rom.headersize, and up here we're going to say self.pc reg. Yeah, it's interesting. So this is going to be set. So currently the PC reg is set as an int. That's going to be an interesting one. Really, since it's referring to binary stuff, it should be hex. Yeah. So we'll set this to 0, and then when we load our ROM in, we'll set it to 16, which is 1. No, 10 in hex. Self.rom.headersize. Can we convert this to bytes? Is there like a bytes.from? From decimal? No. Interesting. Let's find out if we can do that. Really what we want it to be is decimal to bytes. Do a list comprehension. Hex ord B. Oh god. I probably don't want to do that. Yep, bit shifting. Probably going to have to do some of that. Hex X. Structured unpack. God, that's terrible. Okay. I get a feeling we're going to get bit by this sooner rather than later. And the PC reg is actually can be a 2-byte value. Can I add to a bytes? How do bytes work? Let's do some experimentation. So if I say A equals bytes dot from hex F, what? I swear that was how we used bytes dot from hex F. That's weird. Is that doing something wrong there? Non-hexadecimal number. F is not considered a hexadecimal number. Huh. That's weird. I wonder why that is. Bytes dot from hex. Yeah, that's what we're using. Oh well. I'm sure that won't come back to bite us. What if I cast this to an int? Oh man, these bytes things confuse me. Alright, I think I'm not going to use them for anything apart from these instructions. We can easily decode what's going on in the instruction set. I think for here, I'm just going to set the PC reg to be 0. The status reg being binary might be good. I'll leave that to now. I think I'm going to set these all to ints. Just so we don't have to just bit shift by dividing or multiplying by powers of 2. Yeah, that's a good point. I was kind of hoping to get around that because it kind of makes a bit uglier code. Instead of F, is it still one direction? I don't know. SP reg. Yeah, look, I'll leave these for now. Let's find out. Just bit shift. Can I bit shift byte values? These byte values confuse me a bit about what they actually are, to be honest. Yeah, so I can't bit shift by an integer. What can I bit shift? Yeah, so I can bit shift an integer, presumably. Yeah, okay. I'm going to stick with integers and just use that byte stuff for recognizing instruction codes. And then I'll try and figure out a way to do that later. Probably, I guess. Cool. These SP regs and status regs, because they're referring to memory locations, I'll leave them for now. Because I believe if I go to here, I'm not going to be able to bit shift this status register, which is what I want to be able to do, right? CPU.startup. So if I look at the status reg, it's a byte. Bytes 4. Sure. Status reg. Right, but I can take the 0th element, can't I? Is 52. Okay. That kind of makes sense. So I can turn it into an integer if I so desire. Can I? But I can't bit shift the status reg. But but I might be able to bit shift 0. Cool. So I can do that. They're a bit weird though. So I think there's no real need for me to store the PC reg in bytes. I think I'm just going to store it as an integer because everything is byte aligned. So if we add 2 to it, or we add 20, the only thing is we're going to need to have a way to convert from hex to decimal in that case, because we're going to have offsets that are in hex, but we're going to need to do that anyway. So that's fine. This is definitely something we're going to have to come back to at some point, but whatever. Hex versus binary. Cool. So yeah, the things out of the status reg we could just get by bit shifting the turning it into an int and then bit shifting it. Cool. What were we doing? I've lost my train of thought a bit, unfortunately. Well, we've got some status flags. What I might do, instead of making this a number, I might make this a class, and so that way I can put some helper methods onto it, so I can I can do all the bit shifting internally and not have to worry about it. So let's do that, because I like classes. Class status. What I found out, Python 3, so in Python 2 you needed to do object to get the new style Python classes. In Python 3 this is actually implicit, you don't need it. So they're all automatically new style classes, which is just a holdover from old Python 2, really old Python 2 stuff. Cool, so let's just copy this. Because that seems like some useful information to have. Let's say our initial value self register equals initial value. So presumably this is going to be a bytes. So now if I come here, I say self.statusReg equals none, self.statusReg equals status, and we'll pass in bytes.from hex34. That's definitely going to be good, right? That's going to give us our reg. It's going to be a bytes. I think in the new type hinting system as well, if you do this, I believe that tells it that this reg is going to be of type bytes. So I should get into that habit as well. That's a cool kind of Python 3 thing, is these optional function annotations. Right, alright, so what we want to do is have some helper methods on this that'll tell us things like, hey, is, did we overflow or stuff like that. So the thing I'm interested about is that the first instruction we had was the SCI instruction, which is where this all came from, was the interrupt instruction. So what that is going to do is presumably set the interrupt bit on this number. So we're going to need a getter and a setter for the interrupt bit. And I think we're just going to do this all as methods and just do some bit shifting to get all this stuff out. It's probably going to be the easiest way, but at least this way we kind of abstract away from everything else what's actually going on. So interrupt. And we're going to return a bool from this. And we're going to say is interrupt. Interruptible. So the bit that has that is the 0, 1, 2, the 2-bit. So if we shift right by 2, here's a question, is shifting a mutable operation? Is that going to modify our reg value? Well, let's see. I don't know. Statement seems to have no effect. No. Okay, cool, it's not. So if we shift it, this way by 2, now this is a byte, but we know if we get the 0th element, that turns it into an integer representation. Yep. So this is going to shift it by 2, and then we want to return the 0th byte again. What is this actually going to return? Let's find out. A lot of the debugging stuff that I do is like this, where I'll just come through and I'll set up a breakpoint, just mess around with some stuff, figure out what I got to do, and then keep going. And it works, well, I don't know, somewhat well, I guess, for me. Cool. Interruptible. Reg divided by 2. Let's see what that returns. So really, self.reg 0. Self.reg, so it's going to be a 4, which means that in binary, can we do that? Binary self.reg 0. Ah, sweet. But that's actually a string, so it's not really a binary number. So I think we'll just do it by bit shifting. What it's telling us is that the second bit is actually already set. Right? Yeah. So is interruptible should return 2. So what does this return? So it returns the number 13. And if we turn that into binary, we should see that the 0th bit should be 1. And then we could just bitwise AND that with 1. Alternatively, we could just bitwise AND this with the number 5, couldn't we? You need to mask the last bit. Yeah. Do we need to shift though? Couldn't we just mask with the number 5? Maybe I'm wrong here. I'm probably wrong here. This is one of those things. But if we have 0, 1, 0, 0, couldn't we just mask with 0, 1, 0, 0, which is what? 4? No? Fair enough. So the alternative is going to be to shift this, obviously, to be 1. Just mask. So we can just mask? Let's find out. Alright, so if we've got this, we know that this is going to return 1, and if we bitwise AND this with 1, this should return true. Cool. Now if we bitwise AND this with 2, for instance, it should return 0. So what if we wanted to say self.reg 0, the original thing, and then masked it with 4? Ah, yeah, so that's why. Ah, yeah, that makes a lot of sense. Okay, cool. You make a great point. So the reason is going to be if these other things are 1 as well. So let me get a new color. I'm just going to draw down here. So if we have 0, 1, 0, 1, and then we want to mask it with 0, 1, 0, 0, then these are gonna these are gonna line up, but it's still gonna return the value 4. Alright, this is not a big deal. I'm just gonna shift it and then mask it with 1. Makes it a bit simpler because then you know it's either going to return 1 or 0, which is going to be a lot easier to determine if it is true or false. 1, which we can then cast to the bool. Can we cast them in the bool? We know it's going to be 0 or 1, so we could also do a return that equals 1. But I don't see why we wouldn't just cast it to bool. Oh well, let's see what happens if we cast it to bool. My gut tells me that it should return true, right? Well, yeah, let's call that method true. Cool. We can come back and we can test that stuff later, but I think that's fine for now. So actually, by setting our initial status flags, interrupt, our power up state is actually going to set IRQ disabled. So IRQ looks like it is enabled with 34. Unless my conversion was wrong or something. P equals 34, IRQ disabled. Alright, so hex to binary again. $34. Yeah, the second 0, 1, 2 is definitely enabled. 0, 1, 2. Ah, shit, okay. So 1 means that IRQ is disabled. That's fun, isn't it? So it's actually is interruptible. Yeah, okay. It's going to return the not bool of that. Yeah. God, that looks beautiful, doesn't it? Alright, cool. Let's see. Alright, let's just set interruptible. So a lot of the times these instructions are going to do something like set interruptible and stuff like that. And instead of, you know, passing around... so a lot of the time, since Python is white-spaced, you'll see me writing pass everywhere. And that's just, it's like a no-op, essentially. So it's just to get the formatting right so nothing complains before I come back and write it. Alright, set the second bit to 0. Alright, let's do it. So self.reg equals self.reg, and then we'll bitwise OR with a binary value of 4. Yeah, so we can do this. I believe that should do what we want. I guess we will find out. This is probably where it'd be a good time to test code and to write something that can test this stuff out. Bitwise and reset to 0. Bitwise. And to reset to 0. I don't fully understand, to be honest, the real Jagliano. Bitwise and reset to 0. Or we'll set the bit to 1. Or we'll set the bit to 1, won't it? But isn't that what we want to do? We want to set the bit... Oh, jeez. Yeah, okay. You're 100% right. This is meant to go here. So a lot of the time, since Python is white-spaced, you'll see me writing pass everywhere. And that's just, it's like a no-op, essentially. So let's just get the formatting right so nothing complains before I come back and write it. Alright, set the second bit to 0. Alright, let's do it. So self.reg equals self.reg, and then we'll bitwise OR with a binary value of 4. Yeah, so we can do this. Huh. I believe that should do what we want. I guess we will find out. This is probably where it'd be a good time to test code and to write something that can test this stuff out. Bitwise and reset to 0. Bitwise. And to reset to 0. I don't fully understand, to be honest, the real Jagliano. Bitwise and reset to 0. Or we'll set the bit to 1. Or we'll set the bit to 1, won't it? But isn't that what we want to do? We want to set the bit... Oh, jeez. Yeah, okay. You're 100% right. This is meant to go here. This is, we want to set this to 0. Yeah, okay. Right. So we can bitwise OR, and this will turn on the second bit. But to disable the second bit, we're going to need to shift it. I think that's what we're saying, right? Set the second bit to 0. Because we need to AND it. What if we AND 111? Yeah, we could just do that, couldn't we? Couldn't we do a bitwise AND of a binary? Let me just think about this for a second. Nah, it's alright. You've raised some very good points. I have proven to repeatedly be wrong, but that's exactly what I want. So if I have 101 and I want to set this bit to 0, if I bitwise AND that with, with 0, 1, 1, won't that do the job? That will be bitwise, this will do 0. Yeah, exactly. Cool, alright. Sweet, yeah. So we'll do that. So we'll you just bitwise AND with a 0 in that slot, 1 and everything else, whereas if you're going to do set it to 1, you do a bitwise OR with a 1 there. Well, it should be 0, 1. And then this will be 1, 1, 1. Nice. So this will be a bitwise 4, and this will be a bitwise AND of... it'd be nice to write some helper functions that would help me figure this out. The second byte is the one that I want to set, so I really want to do 0, 1, 1, which is going to be 3, right? This is probably bad. Yeah, a bad way to do it is bitwise shifting by decimal values. Probably the better way to do it would be put them in binary and then convert them to int, but I'm not sure that Python can do that nicely. Or maybe it can. Oh, that's fine. Alright, so set interruptible. Cool. So our instruction, unless I'm wrong, let's look up the SEI instruction. I believe what the instruction should do the interrupt flag is used to prevent SEI or CLI maskable interrupts. So set interrupt. Does it have any more information about what it's meant to do? Oh, nice. It sets the I to 1. Cool. So really we want to come back to here and we want to say the execution of sei.instruction is actually just going to set the instruction flag to 1. Why not just create booleans for each of the status bits so you can skip the binary operations? That is a significantly better way than what I've done here. It's probably something to remember in the future as well, to try and simulate things, try and cheat and do things through software instead of trying to do them through hardware. That's a great point. Let's just do that. There's no point doing this. No, absolutely. This is... You will note that if you haven't pointed some of these things out, I would have gone down quite a deep rabbit hole of bitwise logic in a lot of these places, which is probably not what we want. So, backseat programming is fine. Cool. Like I said, I've never done any of this emulator stuff before, so I'm going to get things wrong, for sure. But, you know, we'll try and push through it and figure it out together. Alright, so let's just set some status values. So, negative, overflow, decimal, interrupt, oh, no, self.0. Right, so we have booleans for all these things. We know our initial state is actually just going to be everything is set to 0 with the exception of the interrupt bit. I'm going to name these all bits just so we know why they are what they are. And then this way we don't need to pass in any parameters here. I'm also going to do type bool. I'm going to do this just to get into the habit of doing that. So we're now using the new typing. You would be doing the right thing. This is VHDL Verilog. Yeah, so the only real experience I've had with doing this stuff was creating a processor using creating a MIPS processor in Verilog. So if I do keep doing some of this stuff, I'm going to blame that, having done some Verilog CPU programming before. But you're right, we don't need to actually simulate what's going on in hardware here. We can just, you know, pretend. Getters and setters, we don't really need. We can set them, but there's no real point. Alright, so set the instruction flag to 1. So now here's an interesting point. Here's probably the next big point. We have a status thing. We can get rid of that. So how is this instruction going to communicate with the CPU, going to communicate with the status? So this is probably where we're going to need to do a bit of thinking. Is probably the instruction shouldn't have access to the status register. It probably shouldn't have access to anything. I'm kind of thinking maybe we want to do some kind of intent system, but I'm not quite sure what. Potentially we can just do this pretty simply at the start, but I guess my idea is an instruction should really just store intent and should never change. And the CPU is the one that should apply the changes. How do we do that? Could return an intent or something to say, we want you to modify the status register, or we want you to store this value. That's a bit overkill though. How many instructions does the CPU have? So it has it has 256 possible instructions. It's an 8-bit kind of 8-bit space, but I believe there are only around 150 of them are implemented. So if we look at where is it? MOS 6502. So here are all the things that are implemented. They're around 150. The good news is that most of these are duplicates. So you can see that, for instance, store in A is duplicated like 6 times, maybe more. And the reason they do that is because each of them has a different indexing mode. So, you know, which memory values are you going to access? So if I can implement those indexing modes, they're kind of consistent across everything, then there might only be, I don't know, I'm just taking a guess here, but there might only be 50 instructions that we need to implement. So not a huge amount, to be honest, compared to like a proper MIPS architecture or something, or God forbid, a modern one. Alright, for now we're just going to do this in the simplest way later. Later I'd like to do this much more elegantly, but screw it. So we're going to pass in a reference to the CPU, because we're dodgy. So CPU is going to be a CPU. And we're going to say CPU dot status reg dot. So what's status reg? Status register is of type status. So this will be cool now. If I do this, can this code in here figure out that status reg is now a... Yeah, it can. So that's super cool. I really like that about this new Python typing stuff. So we're going to set the intro bit to true. Alright. Yeah, so there are 150 instructions, but I would say most of them are quote-unquote duplicates. They're the same instruction, but just with different indexing modes, addressing modes. We'll get to that later. But you can see, I mean, there's at least 16, you know, another 10. Yeah, I reckon there's probably around 50. This is probably something I could easily look up, to be honest. I should probably do that. Instructions. I don't even know if this thing has a pipeline. I still don't know that, actually. Whoa. Alright, I don't know. To be honest, I guess we'll figure that out as we go along. You might have to create a CPU class which will have a field that has a status register, and the CPU class would have functions that would cover the instructions. Yeah, potentially. The way I'm hoping to do it is to have a kind of class where my thought is we don't want to be obviously instantiating a new class with every new instruction we find, but if we have a single object that is doesn't really have any state, so we could reuse it for every same instruction that we find, we could do some cool stuff then with mix-ins to do with how we're going to make things addressable, and so we could just have a lot of like reuse code and basically cut out all those like giant switch statements and huge amount of functions that you need to implement every one of them, and just try and do it through some mix-ins and Python magic. That's the dream, at least. Whether or not that's going to be, you know, possible or not. Alright, so we're going to set the instruction bit to true. For now, this is probably a terrible way of doing it. I'd probably want to do this somehow, yeah, like I said, through intents or calling back, but whatever. Now the instruction bit is already true, but I guess it's just ensuring that that is going to happen. So these are actually just refactor instructions, and these are instructions mapping. cool. So if we breakpoint here and breakpoint here, we should see, well, nothing will really happen because we're not doing anything right. Alright, we are importing CPU, and CPU is probably importing instruction. Yeah, so we have some circular importing going on here. I can never remember how to resolve this in Python. I think the answer is just don't import a specific thing. That is a terrible way of doing it, but let's see if that resolves our issue. Module CPU has no attribute CPU. Sure it does. Alright, well, let's get rid of this type hinting for now. Cool, alright, we'll have to figure that out later. The answer is don't do circular imports. So instruction.execute, so we should have a status .interrupt bit, and that should be set to true. Now I'm going to do something dodgy, and I'm going to set that to false. And now when I look at it, it should be false. Then after this instructions run, which is the SEI instruction, it should be set back to true. And it broke. Missing a positional argument. Yeah, okay. Self. So it's true. Let's set it to false. Check that that's worked. Run. Set back to true. Cool, so we have our first working instruction. Not only that, but we have an idea of a status register. We've got some startup state, all this kind of good jazz. Alright. What now? Yeah, so I do want to figure out a nicer way of doing these, kind of implementing these instructions. Hopefully using some Python 3 magic, because that would be pretty cool. Pretty cool indeed. So I'm just going to have to think about that for a second. Is if we, instead of doing this, which we don't really want to do, is like, yeah. Yeah, you might be right. I was kind of hoping to avoid passing in. So my kind of thought, whether or not this is going to be crazy or not, would be in doing that, you could return like a interrupt enable intent or something. And then those different ones, you could push different indexing modes into there and the CPU would interpret them, but really we're just going to be doubling down on the code. Something's got to interpret what that interrupt enable intent does, and something's got to access the status register, whether it's some externally facing functions on the CPU or something else. Yeah. That's going to be a hassle. Alright, for now, let's say that we passed the CPU in. Let's not worry too much about it. This should be something that's relatively easy to fix up later on. Alright, let's see what a CLD instruction is. So that's one down, I'm going to say. That's done. CLD. Clear decimal. So presumably clear decimal is going to set this byte to 0. Yes, nice. So where's my clear decimal instruction? CPU.statusreg.decimal bit. equals true, false. Whoa. Now, a lot of this stuff we can kind of make generic, and we can do with some Python magic and mix-ins to make this a lot more terse instead of being quite verbose as it is now. And then that way we're going to get a lot of stuff. Kind of my thought is there's these different types of instructions as well. So there's addressable ones, and then there's the different types of addressable ones, so you could use that as a mix-in. Potentially there's also ones that modify status. So the ones that we're just doing might get passed to status reg instead of something else, and intrinsically they might modify that. Yeah, well, let's mess around with that a bit and see where it goes. I doubt it's going to turn out very nice, but... So let's say a status instruction inherits from instruction. Actually, if we say it's an object, let's try and make it a mix-in. Let's make it inherit from object. And we'll say that it has... all status objects have an instruction length of 1. So all these commands do have variable instruction lengths. They're known instruction lengths, but they're variable. And we actually want, it needs, what does this status need? So it's going to modify the status object of the CPU. So if we presume that there's a change status or update status, and then this way we might be able to import what we're getting. Cool, so update status. I'm going to make this do nothing. Nah, this is going to have to be, yeah. Alright, well let's make this an abstract method. And it's going to inherit from instruction. It's going to have an instruction length of 1, and its execute is going to have to do something. Execute. Is there anything about a status instruction apart from the fact that it's instruction length 1? Probably not. Okay, so if I did this, if I did object, and then if I did this as a mixin, will this allow me to do that? And then if I don't set instruction length, no, it won't allow me to do that. Damn shame. Alright, that's fun. I guess it's one of those things we learn. CLD. Clear decimal. We have done this. Nice. There's going to have to be a fair amount of refactoring for this, but whatever. Status regs. Whoa. Data regs. Data instructions. Cool. Well, What's the next one? We do an LDA. So if we look up what LDA is, LDA, yeah, so you can see there's 8 implementations of LDA that depend on the indexing. So this is where I'm kind of hoping that the mixins will be able to help us out. Load accumulator. So if I come back to, oh, I don't have it up here. I think it's saved in here. If I come back to this image, I can kind of see that we're going to have 6 registers. This A register is called the accumulator register, and it's going to be what we use when we do any arithmetic or multiplication or stuff. I think the result gets stored in this accumulator register. And if there's overflow or anything, there's a flag that's set for that, so we can keep track of that. Yeah, so we just want to have something that can load a value into the accumulator. Cool. All of this stuff can disappear later. We can, using Python, either dodginess or metaclassing or something like that, we can make it automatically print. We could add like a at debug, whatever these are called, somethings, annotations, something like that, that would just make it print out everything so that we wouldn't have to do this, but for now, it's fine. Alright, so we want to load the value into the accumulator reg. Alright. The other hope is that instruction length will be able to be inherited from the mixin. So eventually we'll figure out how to do that. Load value into the accumulator reg. Right, so CPU dot areg equals 7. So since we have a multiple instruction length here, what we're actually going to have to do is go back and retrieve the next byte as well and pass it into this instruction. So so that we can get the second byte, we can determine what it is, and we can determine what value we actually want to pass into the accumulator reg. First things first is going to be to figure out which command this actually is. So it's an A9 command. And if I look at A9 commands, A9, yeah, we can see it's a load absolute value. So it's only going to be a two byte thing, and it's going to be whatever value is in the next byte, we're going to store in the A register. And in that case, this is going to be 10, which is 16 in decimal. Cool. This system is also little endian, which means we're going to have to deal with that later when we're dealing with bringing in 3 bytes. But I believe when you're just dealing with 2 bytes, like we are now, there's only 1 data byte, which means there's no ordering to the data. It's when you have 3 bytes, therefore there are 2 data bytes, you need to think about your endianness, which kind of sucks, but we'll do that later. Alright, load value into accumulator register. Yeah. So we need a way to pull out the correct number of bytes. So how are we going to do this? We're going to have to do this in our CPU loop. So the CPU's got to know what bytes to pass. So it's going to pull out the instruction byte. It's going to figure out what instruction that is. It's going to execute it, and then it's going to increment the PC reg. Really what we want it to do is to pass in any data bytes that are associated with this identifier byte. And we're going to know this at this point because we know what the instruction is. So I'm going to say that we're going to pass in some data bytes. Now, later on we might have to organize these for endianness, but for now, I'm not going to bother. We have valid instruction class. Cool. Alright, so what are data bytes? So and we actually know how many data bytes we need to pull out because we know what the instruction length is from the instruction. So the number of data bytes that we need to pull out is going to equal instruction dot instruction length -1. Now it's going to be -1 because, for instance, for this 2 instruction length instruction, one of them is the identifier of what the instruction is, and only one of them is a data byte telling you what value to store. So we know how many data bytes we need. Let's find them from the memory and let's pass them in. So we're going to need to access the ROM. Get byte self position. So I implemented this get byte method, which is going to return a single byte. And really what we're going to need is a get bytes method, which is going to be a position. Actually, what it's probably going to be easy to do. Size is an int, and it's going to default to 1. Man, that's really shitty pep bait. I don't know how to format that nicely. Alright, get bytes at a given position, and we're just going to return the correct amount of bytes. So now when we request a number of bytes, it'll return however many we need. I've changed this name, so this is going to be get bytes. So it's going to be a bit shit because we're going to have to do it once here to get the byte to identify it, and then we're going to have to do it down here once we know how many bytes to get. So potentially, probably what's going to be smarter to do eventually is you're going to read in a chunk of bytes. You know, you might read in like a kilobyte of bytes, put them in a list or something, and then you can much easily access them. But, I mean, this is just like an array access anyway, so it's not really a big deal. It's kind of a very late in the game thing. Cool. So we want to get the bytes. And we want to actually get them at the self.pc reg. So we don't care about the instruction byte anymore. Because we've already got the identifier byte. So we're actually going to move forward 1 and start getting the data. Get the data bytes. And the size is going to be number of data bytes. So potentially this could return, if there are no data bytes, this is going to return none or an empty bytes or something. So what I'm going to do is I'm going to see what it actually returns because I'm curious. I need to store that in a variable. So let's just paste this in here and see what happens. Yeah, so it's going to return an empty bytes, which I don't really like. But whatever. Let's say data bytes. Cool. Alright, so now when we execute CPU data bytes. I probably should just refactor all this stuff because it's easy to do with PyCharm, but whatever. Alright, so we don't care about the data bytes here because we know that they're going to be empty. Potentially this is something we can do with mixins later if it's going to know that it doesn't need data bytes passed in, but whatever. Data bytes don't need anything, data bytes don't need anything. Here we know that there should be an instruction length of 2, therefore 1 data byte. And this particular instruction is load A immediate. So we're loading a, I'm going to refactor, load A immediate instruction. And we know that that's going to take a value, the first value in the data bytes. And there should only be 1 value in the data bytes, but let's see. Oh, CPU data bytes. Oh god. I'm just going to stop calling this super. Caused me too much pain at the moment. Cool. Instruction.execute. Why am I breakpointed there? No reason. Alright. So, loading the value into the accumulator register. A reg should equal data bytes 0. So what happened? What's in data bytes? And so we looked at this before, and we said it should be 10. So this is our A9. This means LDA, and this 10 is going to be the data that we're going to store in that. We can see it is indeed 10. And if we say data bytes 0, this is going to turn it into an int, which is 16, which is what we expect. And our register, and now if we look at our self.areg, should have a value of 16, which it does. Awesome. So we now have 3 working instructions, which is pretty cool. These are finished instructions. They're not, really finished, but, they're implemented for now at least. So we can see what they're doing and, know that at least something's going to happen. All right. Cool. PC reg is being incremented correctly. Console is doing nothing. Yeah, let's see what happens. Instruction not found, which is what we wanted. We've hit the next instruction, and I should print out what those identifier bytes are so that we can know what the next instruction that we can find is. Cool. 8D. I'm just going to check and just make sure that we're on the right path here. 8D, that is indeed correct. So let's look up 8D and see what that is. 8D. Where is D? Store in A. Absolute. No, store from A, I guess. Store A. Absolute. Is there a way to make this? There we go. Case sensitive. Alright, so store absolute. This is what we want, 8D. So it's going to be 3 bytes, 4 cycles. 4 cycles. So we do have a pipeline? Well, haven't implemented that yet. Alright, so absolute 8D. So store accumulator in memory. So we're going to go A to M. So we're going to store the value that we just put in there, which is 16, and we're going to put it somewhere in memory. So it's going to be 3 bytes. 3 bytes, okay. So what I'm trying to do here is get a bit of a base of instructions up, maybe 5 or so, and then start figuring out the common components between them and start doing some fancy stuff. But for now, we're just going to keep on trucking, implementing some more instructions. So class is going to be store A, and it's a absolute instruction. It's going to inherit from instruction. The identifier byte is going to be 8D instead of D8. Cool. The instruction length is 3. So why is the instruction length 3? So we're doing an absolute operation. What's that going to mean? So absolute operation means that we're going to have an absolute value in memory to store this in. So it's going to pass in 2 bytes, and those 2 bytes are going to tell us somewhere in that 65 KB that we can reference which byte we should store this byte in. There are other ways of doing it. So you can do offset, which I think is called indirect. So you can have an offset around you, or you can add other registers to what's going on, so on and so forth. Cool. 3 instructions. So automatically we should get past the correct data. So let's just go to here. Let's just check something here so I can breakpoint it. This is not going to work because I haven't registered it. but this is one of those bugs that you figure out just before you hit the wrong button. Right, so now we should get to here, and the data bytes that we should get in, there should be 2 data bytes. So this doesn't really tell us much, this view of it, because there's not a particularly useful representation. What is useful to us is if we say data bytes 0 and data bytes 1. So what it's telling us is that this 8D should have 2 numbers after it, one of which represents 0 and one of which represents 32. So there's the 0, and 20 in hexadecimal is indeed 32 in decimal. Cool, so our data collector is working correctly. Now the only thing is, data bytes 2 should be out of range. We need to know the correct amount of bytes, but we do know that because we know the instruction link, we know the instruction that we're doing. So that's fine. Cool, so what do we actually want to do here? So we're going to take a value from a reg and put it in memory. Now, I talked about endianness before. So what little endianness means is that this instruction is 8D0220. What it means is that the least significant bit is first when you're formatting some data, like an address. So when you're talking about the data, which is 0020, they're actually going to be flipped when we... so the 00 is meant to be the least significant bit. So if I kind of copy this over here, really what this is saying is that the address it wants us to store it in is actually going to be in hex 2000. So you flip this byte with this byte, keeping in mind that hexes come in 2 for 1 byte. So you don't flip them internally, you flip them in packs of 2. So 0020 becomes 20, which is this one, and then 00 becomes this one. I think. I guess we'll find that out soon enough. All right. So we say that the memory address equals data bytes 2. We'll need to figure out how to plus data bytes 1. I'm not sure. Oh, actually, this should be 1 plus 0. I'm not sure how we can cat bytes. If that's, I doubt that that's going to work, but you never know. So data bytes 1, data bytes 0. So what if I did data bytes 1 plus data bytes 0? 32. So it's going to add them. It's probably not what we want because they are just ints. We're going to have to figure out how to flip them as bytes. And the answer is probably going to be doing some byte trickery. So if you kind of look at the bytes, 0, 0, space. Yeah. Alright, I think this is the point where I'm going to do some Googling on this. So, Python byte endianness. Interpret bytes as packed binary data. Oh, this seems really useful. Python values and C structs represented as Python strings. Binary. Ah, that's binary data. Okay, I probably don't care about that. I could store it as this. Ooh, let's try this struct thing and see if it works. One cool thing about PyCharm's, this debugger, is you can do import statements in there, and then now we have access to struct, I think. Required argument is not an integer. Cool. So how do we actually use this? Struct, not stack. So this is going to take us a bit of time, I suppose, to figure out, but returns a byte object containing the one packed according to that. This is exactly what we want, right? These arguments must max the value. Okay. Pack. So alternatively, the first character of the string can be used to indicate byte order, size, and alignment of the character data. Well, we want it to be little endian, or maybe we're packing as big endian. Anyway, let's figure it out. So that, and then instead of an integer, we want to say it's, where's the byte? Pad byte? Char? Is it a sign char? I don't know if it is. Great point. Let's just say it's a char. Let's find out. Char requires a byte object thing 1. S. Python value, bytes. Alright, how about S? Well, that did something. So that's a first. What if I did that? Cool, doesn't seem to have any effect. So let's open up these bytes and let's see what the 0th byte is, because really it should be 32. No. No, so that didn't work out for us. Huh, okay. Interesting. Changes the endianness of bytes. Just open up some threads, find out. I have a binary file, I'm reading some 2-byte files. Yeah. Ah. So what if I did 2C? 2 items for packing, got 1. What if I did dodgy and dereference that? Char format requires a byte object of 1. Can't remember how to do that. Alright, so what if we did data bytes 0, data bytes 1. Char format requires a byte. Yeah, okay. What if I did 2? Alright. Yeah, well, that's interesting, isn't it? Right. Okay. So what we actually want to be doing here, I might do this somewhere where everyone can see it a little bit better. What we actually want to be doing is taking the first byte, not as an integer, but as a byte. So data bytes 1 to 1. So this is how you get a byte out, right? No, it's empty. 1 to 2. So instead of returning an integer, I want to return a byte. Yeah, so this is the second byte. Then this should be 0 to 1. Some dodgy things. What if I did that? And then I did the 0th byte of that. Is that going to be 32? Oh, shit, yeah. Holy crap, yeah. We did it. Cool. So, after all that, the answer was flip them by pulling the first byte out and the second byte out, and then adding them together. The problem with bytes in Python is that if you pull out a value, so if you did data bytes and indexed it by 1, it's going to give you an integer. If you do 1 to 2, it's going to give you the byte that is in that position. Whew. Yeah, that was interesting. All right. So we've got our memory address, hypothetically. Let's see what that gives us. Yeah, space x00, which isn't very human readable, but we can turn that into hex if we did want to. Memory address dot hex is going to turn it into 20,000. Cool, which is what we would expect because this 20 and this 00 have been flipped to make 2000. Cool. Alright, well next, let's store it. We don't actually have any memory yet because we haven't done that yet. So let's do that. Memory. Kind of as we go along naturally, the next obvious thing to implement will pop up, and then we can implement it. I think there was a to do somewhere here. Yeah, to do make memory. That's always good to do. All right, so we're going to make our RAM. So the RAM on the NES is made up of 2 kilobytes. There is 2 kilobytes of RAM. There is also some other memory, and we saw that there's some mirroring, so to reduce the complexity of the maths a bit. But at its core, there is only 2 kilobytes of RAM. So what is 2 kilobytes of RAM? It is a kilobyte times 2048, right? I think. So let's implement that many bytes worth of memory. Now, the way to do this is just going to be to use a list. And then just have some access methods that will do some out of bounds checking for us. So we don't actually have to specify how much RAM we have. Anyway, so init self dot memory equals an array. So this is going to be an array of bytes. So again, Python 3 with this optional type checking, there's a new module called typing, where you can import things like list. And it's actually going to be a list of ints. So we'll do overflow checking and all that stuff manually instead of bothering to store them literally as bytes. Because bytes suck. Cool. So we now know it's a list of ints. Alright, and it's empty, so it doesn't have anything. We should probably just populate it with with zeros. Now, how do we do that? I forget. It's like this times something. If I do that instead of breakpoint there, is that going to work for me? Let's find out. So I think the CPU should own the RAM. Should the CPU own the RAM? No. Let's create the RAM and pass it to the CPU so it can take control of it. Alright, RAM equals RAM. And then CPU should take control of the RAM. Here. RAM, which is going to be a type RAM. Self.ram equals RAM. Cool. So if I do this, let's figure out if our memory is actually going to be what I expect it to be. Yeah, it's a list. So if I did that, is that a list, class list? Looks the same to me. So I think that's how you do it. I'm sure it's going to be wrong. It's going to come back and bite me later, but whatever. Alright, def, we want to access some memory. So we either want to get a byte or we want to get bytes. Now I think at the moment we probably only want to get a byte. Similar to the method that we have on our ROM, which is, you know, well, let's just steal this. Except it returns bytes. Interesting. Maybe we do want memory to be bytes. Huh. That's going to be an interesting one. I suppose that's something that we can easily change later. Hopefully, you know. Byte versus int? Question mark? Cool. Alright, so let's get a byte at memory location. So self.return the memory location at the position. Now when that is, this is assuming that we have an integer, or I suppose I should say a decimal position passed in. So we just need to be careful about that, because at the moment we have all our values are in hex. Yeah, which could be an issue. Anyway, KB equals 1024 times KB times 2048. Right? Wait, no. How much do we have? 2 kilobytes of RAM. Oh, shit. Times kilobytes times 2. Alright, so we have 2 kilobytes of memory now that we've physically created in Python. That's just storing an int for everything. Get byte at position, return this. It's going to return an int. I kind of wanted to return a byte. I'm going to do that. Can I just do that? There's no way that's going to work, right? Well, that's pretty cool. What the hell does self.memory equal? Is it just blank bytes? Class bytes. Oh my god, that's weird. Alright, what happens if we access self.memory 0? Does it give us back a byte? It's a class bytes. Okay, yeah, that makes sense. From hex 0. Is there an easier way to instantiate a byte to be 0? Probably. Yeah, that looks way nicer, doesn't it? So, full of 0 bytes. And this is actually going to be a list of bytes. Now, sorry about that. Alright, so our memory our memory is going to be full of bytes. Sick. If I restart this now, I should be able to see that memory 0 should be an empty byte. And I should be able to turn that into an integer, which is 0. Which I cannot because it's an empty byte, not a byte saying 0. Right. Alright. Non-hexadecimal number. How is this non-hexadecimal? Well, let's look up byte stuff from hex. I evidently don't understand what's going on there. It's a bit of a mystery. Byte array. I don't know. Alright, that's good thought of something we'll have to come back and fix. At the moment, let's make it storints. Whatever. Cool. So we will now come back and we will take a look at our code over here. And this code is going to find that memory address. We want to then convert that memory address into something that's indexable in our memory system, which is going to be decimal, I suppose. Yep. Alright, so at the moment when we get down to here, what do we actually have? Do we have a... We've got a memory address, and the hex is 2000. And what if I say int memory address? What are the odds of that working? Not great, hey. Haha. No, that is not what we want. Alright, so we're going to need to figure out how to... Yeah, the problem is at the moment we're dealing with everything in hex, and at some point we're going to need to deal with it in not hex, so that we can figure out where to get this memory from, or where to put this memory. Cool, so where do we do that? I feel like this is a recurring problem. Python bytes to int. That did not work. Right. The string of bytes. Cool. Oh, jeez. Whoa, that doesn't look very nice at all. This doesn't work for arbitrary linked binary strings. God. Well, we don't actually care. Ah, int.fromBytes. Holy crap. That's what we want, hey? And in fact, that way we don't even have to check the endianness. So if we said int.fromBytes data bytes, and the byte order is little, 8192. At 0020, so in hex it's 2000, hex to binary. Is this gonna just fix everything? I can't do this math, so 20,000, 2,000. Ah, you're kidding me. Hex to decimal. God. 8192. 8192. Oh my god. Alright, this is what we want to do. So we want to take these bytes, we want to take these data bytes, we want to put them in little order, we want to cast them to an int. This is now our memory address. And we want to then pass this. We want to store a value in the memory. So we want to say we want to say CPU.ram dot get byte, and actually we want to set a byte. So let's set up a set byte function. Self.memory position equals byte. Position byte. We'll come back and do some typing for this in a bit, just to make it nicer. Memory address. And we want to store the value from the areg. So vel to store is going to be it's going to be the CPU areg. Now what's the CPU areg? It's actually a 0 at the moment, so it's an integer. Alright. It's an integer, and we're storing that. Vel to store. Sweet. Okay. So now if we keep running this, when we raise... set byte. When we raise an exception... that's fun, isn't it? Position. What's going on here? Position is 8192. Oh god, yeah. So we talked before. It's trying to store it in 8192. I'm just going to close some of these tabs so I can find what I'm looking for. And we talked about the memory status, or the memory of what this this NES dev looks like. And the memory map, that's what I'm looking for. So this value 8192 is 2000, which is actually going to be in our PPU registers. So it's not even addressing something in our RAM. So it's going to be looking at something in our PPU registers. So what we're actually going to need to have somewhere, probably in the CPU, is something that maps an address to the correct component. So if it's below 2000, it sends it to the RAM, and if it's above that, it'll send it to either the PPU or the APU or whatever the appropriate component is. So it's storing the value 16 in the first slot of the NES PPU. And now if I had to take a guess, that's going to mean something. Controller 2000 write. Right. So the PPU has an internal data bus. Oh yeah. Okay, decaying. We're not going to worry about that for now at least. PPU control register. Access right. Yeah. Okay. So this is a flag that we're setting to be 16. 4, 8, 16. So we're setting this bit, to be 1. Background pattern table address to be 1000. Right, so the reality is we're already doing PPU operations and stuff like this, but at the same time it's just memory that we are writing to, but it's memory that the PPU needs to be controlling, and because it's to do with the PPU thing, so on and so forth. So we'll have a class that can just read from, called status, that can just read from that thing. Because we're physically writing to memory, I'll probably implement it as a memory write. Although alternatively, the CPU could just know that this is going to be a thing. For now, I'm going to write it to memory. Cool, so this thing should actually not be accessed because the byte is not in RAM. So how are we going to know that? So we're going to need to tell the CPU to know that. So the CPU is going to, what's it called, a TLU or something? So we're going to need to have some kind of lookup. So when we're storing memory, I'm going to call it a memory map for now. Whether or not that turns out to be a good idea. As always, we can fix it later. So return the owner of a memory location. So probably what we're going to have to do is to define some kind of interface that says you have memory locations and here are some functions with which you can access them, so that RAM and ROM and all this kind of stuff will implement it. This function on the CPU will return one of those interfaces, and then you can call get or set bytes on that particular bit of memory. And potentially if it's ROM, it'll throw an exception if you try to set a byte or something. That's probably how it's going to have to work. Alright. Cool. Let's keep going then. So at the moment, if so we'll need to pass it, we'll say memory owner, get memory owner. So we'll get the memory owner, and you need to pass in a location, memory location. So if, and this is probably going to be passed in as an int or as a byte. So I guess the question is, we need to do this decoding somewhere of from bytes to integer, but potentially we don't need to do it yet. Potentially that'll just be done by the memory or by whatever. So we might as well pass it around as bytes, just to be a real tripper. So if location, how do I do a comparison on a bytes? Great question. Maybe it's not best. Maybe I should just convert it immediately to integer and then not have to worry about it. Yeah, I might do that. So let's say that a memory location is going to be passed around as an integer. Yeah, alright. So if the memory location is going to be greater than, so now we're going to need to, alright, so we know that if it's less than or equal to, yep, alright, less than or equal to, where's my memory map? Here we go. If it's less than or equal to this 1FFF, then it's actually going to be routed to the RAM. A191. Now I could actually store these as constants because I can now do this. Which is pretty cool. int.fromBytes, cool Python 3 thing. Let's do that. Potentially the RAM should define this, but for now I'm just going to put it up here. So int.bytes from bytes, and we want to do bytes.fromhex. Beautiful. To what was it? 1FFF. So that's the last memory location for the RAM. RAM and inclusive. Right, so the RAM ends there, but it includes that value. So if the location is less than or equal to RAM and inclusive, return self.ram. else if location. Yeah, okay. So we're going to need to do a RAM start. Parameter byte order unfilled. Okay. So I need to fill in a byte order equals big, presumably. Yep. Okay. So we're passing them in big endian format. Here, where does our PPU start and end? So this is our PPU memory. So potentially when we make the interface saying that these things can control memory, this is where they will get moved. But again, I'm just going to put them here for now. Oh, memory map, PPU 2000 to 2007. Okay. Inclusive, presumably. Two 2000 to 2007, and these are just registers. So potentially in this 2000 to 2007 thing, like I was saying, instead of storing it in memory, we could just route it directly, because we don't actually care whether they're stored in memory or not. Oh well. So if RAM start inclusive, now I believe that you can do that, right? If location is in between those two, return RAM. And then if it's in PPU start inclusive, send it back that way. PPU end inclusive. Return self.ppu. Actually, I think at this point we would just pass off to the PPU register manager. And we're just gonna pass that. Now we'll return the PPU register manager, but we'll make sure that it internally doesn't bother storing memory. So we're going to need a PPU. Cool. Let's create a PPU. That's going to be a new class. Because we do love new classes. And at the moment this is going to be empty. Create PPU. So RAM PPU. Nice. Alright. PPU is a PPU. Duck is a duck. Alright. So we now have a PPU. Sweet, what do we want to do with the PPU? Great question. We want to return it self.ppu and pretend that this is a memory owner. So what does a memory owner do? It's going to be something we inherit from, or ideally we mix in from. Because that's going to make our life a lot easier, a lot nicer. Because then we're going to have some defined functions, and we can annotate what we're returning from this function is going to be a memory manager or something. At the moment we can't do that, but we will. We will someday. Cool. So we assume that we're getting in data in an int. Rock on. All right. Velta store is CPU A reg. Yep. And we want to set the byte, not of the RAM. We actually want to get the memory owner equals CPU dot get memory owner for a memory address. So this is the kind of stuff where we're going to be doing this commonly in a lot of operations, you know. And so this is where I want to be doing this kind of mixing stuff, where I can just say, hey, you're something that gets or sets memory, you have this kind of addressing, and you take from this kind of location. But like I said, that's kind of a, let's implement a few and then see what commonality we can. And we're going to have to pass, what is, RAM. Interesting. Let's look up Python mixins abstract. Can I do abstract mixins? Is this going to be a bad idea? So you've got a bar foo mixin, bar foo bar mixin. Right, so mixins have got to go to the right of views. Yeah, so I think instead of doing this, we're going to implement this as a mixin. And then that way we'll actually implement the get byte functionality here. And then anything that wants to inherit from this will have all of that automatically, maybe. What are you going to use for graphics? Good question. So I have in the past, a long couple of years ago, I messed around with Piglet a bit. And then let's look up Python mixins abstract. Can I do abstract mixins? Is this going to be a bad idea? So you've got a bar foo mixin, bar foo bar mixin. Right, so mixins have got to go to the right of views. Yeah, so I think instead of doing this, we're going to implement this as a mixin. And then that way we'll actually implement the get byte functionality here. And then anything that wants to inherit from this will have all of that automatically, maybe. What are you going to use for graphics? Good question. So I have in the past, a long couple of years ago, I messed around with Piglet a bit. And then it kind of stopped being maintained, and so I stopped using it. But it looks like it's started being maintained again. So potentially Piglet. It was kind of nice. It had a nice API for drawing stuff easily, and if you wanted to go back to your just old style OpenGL calls, it worked for that as well, which I really liked. So you could kind of do whatever you want. I've used Pygame a bit as well, but I don't really like it, to be honest. It seems quite slow, and yeah, Piglet just seemed nicer when I used it, at least. But this was a few years ago, so things might have changed. Also Python 3, I'm unsure which of these libraries are actually compatible with it. Potentially all of them. Yeah, so where did I implement get byte? I implemented that on the ROM, right? Yeah, nice. So a memory owner is going to be able to . self.getBytes. So we'll just have to create some things here that will have to be implemented by the person. By the class, sorry. Can I have an abstract method on a mixin? It's an interesting thought. Abstract method you have to define when you inherit from ABC, blah blah blah. I actually don't fully understand what mixins are going to do for me. Let's find out. Typically narrow in scope, not meant to be extended. Yeah, so you inherit from the base class. Alright, cool. Let's just do it. So self.getMemory. Let's presume that getMemory is going to return an array. Right, so I'm kind of cheating there, but if I do, I'm just going to do a test here. So my memory owner is going to be object memory owner mixin. So if I do that, and then I say definite self.getBytes position 0 size 1, and that should return to me a byte. Cool. My byte x equals 1. So let's see what this actually gives us. I'm just going to do this because I kind of just want to know what's going to happen. My memory owner. Alright, let's find out what the mix-in order is. Yeah, okay, sorry. So it's mix-ins the other way around. So my byte is going to be 1. Cool. Now if I define a get memory function and I say return 2222, is my byte going to equal 2? Yes, it will. That is awesome. So all we need to do is override the get memory. We could manually make this abstract by saying like raise exception, you need to implement this, but that's kind of a shit way of doing it. If I do that, is that going to work? Do I need to make that? That's going to work. What if I... Whoa. What if I get rid of that? Yeah, it doesn't do anything. What if I make this inherit from ABC? It should error out. Can't instantiate abstract class. Yeah, and so now if I define my get memory method here, then it should be return 222. Sick. This is what I want. All right, so we're going to have an abstracts class mix-in, which is probably a terrible idea, but whatever, I'm doing it. So basically the thing you need to implement is going to be a get memory function, which is just going to return what your internal memory set is. And it's going to tell you how you can get bytes and how you can set bytes. And this means that all our byte access between all our different types of memory is going to be the same. So we're going to set byte at position int, and we're going to set it to a value, which is going to be an int for now. Bytes. So ROM actually deals in bytes, which is interesting. The other memories may well have to deal in bytes as well. Alright, so typically it's going to be a single bytes, because you're setting a single byte. Oh, let's see. So self.getMemory, and we want the thing that's at position, and we want to set it to value. We need to assert here or check that bytes is only a singular byte. I'm just going to do that. If len bytes is greater than 1, this will save us later on when we do something stupid. Alright, because this bytes type is a bit weird because it can be multiple or single, we'll probably need to do some checking. Alright, let's keep going. So we now have this memory owner mix-in. Let's make our RAM use it. In fact, let's make our ROM use it. So it's got a mix-in and it inherits from object. Nice. All this stuff, this is fine. Pulling out its ROM bytes is fine. Now what methods does it need to implement? It needs to implement the get memory method, because otherwise it's going to have a bad time. And it's going to return its ROM bytes. And now this get bytes and set bytes functionality is inherited for free. And what we're also going to do is we're going to override the set byte functionality. We're going to make it return an error because this is read-only memory. Trying to nice. Potentially we could just separate this out into a read and a memory reader and a memory writer and inherit from them both. But since most things are going to be read and write, with the exception of the ROM, I'm just going to make it do that, and then the ROM can raise its own exception. There are multiple ways of doing that, I suppose. Alright. Cool. What's next? So we get the get byte functionality for free. The set byte functionality, we're just going to raise an exception. So that way we know we're never going to write out read-only memory. That's pretty cool. So memory, this should probably be called RAM instead of memory. Alright. So this is going to inherit from memory owner, mix-in, and also from objects. Now, its memory is, at the moment, is a list of ints, but we're probably going to have to change that. So def get memory, it's going to have to return soft.memory. And get memory should return a list of bytes, right? I think. Good. Over here we were looking at our ROM before. We're going to want to make sure that all our things are consistent. So this is also going to return some bytes. No, list of bytes. Now, what it's actually going to be is a list of singular bytes. But that's fine. All right. Get memory, RAM. Okay, so what's our RAM going to do? So our RAM is going to return a list of bytes. This is going to have to be a list of bytes, because that's how we're doing everything now. And this is going to have to be a 0 byte is bytes dot from hex. I've already tried this, haven't I? Good. 008. Alright, what happens if I do that? A 0 byte. Zero byte 0 should be 0. And 0 byte 1 should be 0. Oh, because you need 2 hex characters to represent a byte. Okay. Yeah. That is an interesting thought. Alright. So now if I do 0 byte, and if I go down one line more, self.memory should be a list of bytes. So self.memory 0 should return a byte, and self.memory 00 should return an integer. 0. Nice. Now what if I do, just out of curiosity, do we get overflow in this? I don't actually know if I want overflow. It's a byte. Can I add things to that? Do I have to add other bytes to that? Can't concat bytes to ints. Yeah, fair enough. So if I add FF, oh god, that didn't work. That physically added it. How do I sum things? Alright, well, worry about that later when we need to do arithmetic operations. Alright. Get byte is going to return a byte. Actually, these things, these are now part of the memory owner mixin. So we can now just, yeah, the only thing we need to input is get memory. Cool, which we've done. That seems pretty nice. Memory owner. So now, if I come back to the CPU, I know that this is actually going to return something that inherits from a memory owner mixin. Right? Because both of these RAMs, oh, and PPU, we haven't implemented either. But the PPU is also going to inherit from a memory owner mixin, among other things. Cool. So what does the PPU need to define? The PPU needs to define this getMemory method. I wonder if I do this. How do I... Whoa. Nope. How do I override methods? I've forgotten the key binding for that. Is there a generate? generate override methods. Get memory. Nice. Nice. PyCharm is really good at this kind of autocode generation stuff. Cool. We don't actually want to return super.get memory. We want to return our own memory. Now here's the thing. We don't actually want to... The PPU is going to cheat a bit, and it's not going to maintain its own memory. It's going to pretend to maintain memory, and it's going to overwrite its own bytes, get byte and set byte, to maintain its status. But for now, we can actually just represent it as memory. And they're actually just kind of like registers. We'll do the same thing that we did over here in the RAM. And I believe that we need 7 of them. I'll have to check that. So what is the PPU registers? Were somewhere over here. So 0, 1, 2, 3, 4, 5, 6, 7. Always good to count out those kind of things. Yeah, there are 8 of them. Right. So there are 8 bytes registers, and now we get free stuff for that. We can override their accesses later, so as well as being stored in memory, we can chuck into some status registers that we emulate. Cool. So, memory owner mix-in. That worked out really nicely. I'm very happy with that. So, what else do we need? Yeah, this is another thing we can put in here. So, these things can just become part of the memory owner mix-in and have to be overwritten. And you can just define what your RAM start and end are, and then that way we don't have to do it here. Cool. Because we know that everything that can be accessed, everything that has memory, needs to start somewhere and needs to end somewhere. So we're going to say it's an abstract property. Def memory start location. Cool. And then we're also going to have a memory end location. And these are going to be inclusive, because that's how I'm going to do it for now. All right. This mix-in is now going to need... all the things that inherit from this mix-in are now going to need to implement these, which we've kind of done here. So RAM. So if I take RAM over here, it's going to need to have 2 more properties, which are going to be memory start location and memory end location. Okay. Whatever. When implementing as properties, we'll just implement as memory start location equals that, and memory end location equals that. Cool. So there's RAM done. So now RAM, instead of having to be done like that, we can now simplify this, get memory owner check, and we can probably push this functionality off to something that automatically generates it. Getting cool, hey? So the mix-in means that it needs to implement these, and the PPU is going to start at 2000. We could also do some assertions and check that we have the correct amount of memory based on what values we're passing in here. But I'm not going to do that now. So we don't get any off by 1 errors or anything like that. Cool. So this function, we now just need to have a list of memory owners, and we could just iterate through them. And we could this check is the same for everything, right? We can just call the memory start location memory own location. So what are our memory locations? They're just things that inherit from memory owner mixin. Now there's probably a way to do this by gathering every child class of memory owner mixin. Can you tell me why you're using those int from bytes functions for your RAM start and end locations instead of just setting it to 0x0 and 0d0 for your PPU? Yeah, it's a great question. I'm still struggling a little bit with this bytes hex kind of distinction. So what are you talking about, the PPU? So currently I'm doing it of all memory I'm storing as bytes, you know, for better or for worse. That might change. But my memory locations I am converting to ints so that I can reference an array. So that's the reason that I'm doing this, is so that when I reference an array, it's in decimal, which is going to be what I can reference the array in. Because I don't believe that I can reference an array with a hex value. I'll need to convert it to integer. I could be wrong about that. But essentially what I'm trying to do is define values in hex here, so I can kind of read them in hex, but know that when I want to reference them as part of an array or something, that I can you can reference them with those hex values. Interesting. I feel like I still lack an understanding of how hex is going to work in Python, which is interesting because I've been doing it for a while now. Handling hex numbers. Can you reference into an array with a hex value? Your way seems to be working fine too. Yeah, it's going to fall apart at some point, I'm sure. So if we can, you know, fix it up now. To the Google, exactly, yeah. Like I said, I'm learning as I go here. I've never done any of this kind of stuff in Python before. Or I've never done any emulator work before. I've done some CPU stuff, but... So I'm a little bit rusty on how hex numbers work. Right, so what it's telling me is that hex 2345, so that's going to take in an int, going to turn it into a hex string. Yeah, so that hex string is actually a... Well, let's check this out. What if I do hex of 10? No, hex of integer 10, sorry. Now what if I do 17? Yeah, so this is going to be 0x11, and it's actually a string, so it's not even a byte. God, okay. I think this is something that might have changed a bit in Python 3. Because you can see in Python 2 it seems to be returning a bytes representation. Int. Ah, cool. Int hex 17 base 10, and then if I say that this is base 16, nice. 1 times 16 plus 1. Great question. Let's try adding something like OXF and 1. So if I do hex 15 plus hex 2. Yeah, it's just string concatenating them, which is always fun. Is this what you mean by... I mean, this is how you would convert to F, right? 16, right? That'll give you... Oh, sorry, 15 will give you F, my bad. Or we can also have bytes dot from hex 0f. Which will give us this, but then we can't add bytes either. Don't use the hex. Yeah, okay. Let's get rid of that then. just print 0xf. Oh, you mean like literally? Oh shit. Okay. Right. I did not realize that we could do that. That is interesting. So what? Right. Okay. So what you're telling me is that instead of writing this, I could just write that. You are completely correct. I did not realize that there was a native built-in for that. That is incredibly cleaner. Thank you very much, Besh. That is, yeah, okay. Well, that's going to simplify some things. Let's put it that way. I'm still a bit confused, to be honest, on how this whole interaction works, because I mean that's converting it to an integer, but storing things as bytes. Maybe I should just store everything as ints. We'll figure it out as we go, I suppose. I'm learning. All right, ROM. What does the ROM start? Lots of crazy stuff just works in Python. That is true. Yeah. Oh well, we'll see. Yeah. Cheers. Cheers to both you and Jay Sudlow. Jay Sudlow. Thank you. Alright. True. What now? So now we kind of want to make this method that's going to be able to iterate through our memory owner mixins and and give us back what we need. So how do we define a memory owner mixins? I'm just going to define it manually for now. Memory owners, and then as we add more things, we can add to this list. Like I said, we could do it using meta classes and stuff, but I'm going to try and be a little nice with that. Just store all your bytes as an array into memory, and you can pull out into individual bytes. Yeah, that is what I'm doing at the moment, I think. I think that's what the memory, so for instance, the RAM is defining an array that is full of singular bytes that I'm loading from hex to be the value 0, because I don't know any other way to initialize the bytes. But whatever. So we're loading the 0 bytes. We actually just have a list of bytes, and then we can pull back a singular byte, which is still looks like... The problem with bytes is that there's no singular. So one single byte is still represented as a bytes object. So we have a list of bytes, but each one of those bytes in that list is just a single byte, which is, yeah, a little bit shit, but oh well. So for memory owner in self.memory owners, if memory owner dot, so self.memory owners is going to be, so I think this is how the syntax works. Oh god, I don't know. Here, type is a list of memory owner mixins. So now when we come down here, autocomplete should... No, that didn't work. Can't you do 0B0? 0B0. That's a great point as well. Let's find out. That would also change things. Ah, that's awesome. But 0B0 is also returning an int though. But still, that's kind of going to be handy if I want to figure out what that equals. Yeah. So that's going to return an int still though. All right. well, memory dot start location has got to be less than or equal to location, which has got to be less than or equal to memory owner dot memory end location. I'm unsure why the autocomplete is not working here, but oh well. Return memory owner. And if it's not there, raise an exception saying cannot find memory owner. Python treats hex and integers exact same. Yeah, and binary it looks like. So yeah, the problem is that everything is coming in bytes, which are a separate concept to hex in Python, I feel like. So I'm kind of treating things as bytes at the moment, but it might not be a good idea. It's not too intrinsic to what I'm doing here, so I'm not too worried. Memory owner. Can I do that? No. Okay. Well, alright. Nice. What happens if I run this? What happens? You just concatenate the 2 bytes. Right? Well, when you have no, I'm sure there's a way to do it, but just adding them isn't going to do it. We're going to have to use kind of. There's a variable amount of bytes that you need to pull in depending on the instruction. Is one thing that needs to be thought about. And we need to flip the endianness of the later bytes. So to give you an example, this 8D is going to be the load instruction, and then we actually want to be reading into the memory address not 0020 but 2000. So we kind of need to read it in byte form and then do some like manipulation to change the endianness of it, and then deal with that address as an integer. And sometimes we need to pull more or less data after this instruction byte. Whether or not that answers what you're saying, I don't know. Hopefully it does. All right, ROM can't create the ROM. Can't create the ROM because we didn't implement the methods on it. Thank God for abstract classes. All right. Where does the ROM start and end? That is a great question. And we will need to come back to our memory map. And we'll say the ROM starts here. And the ROM ends here. So this is cartridge space, PRG ROM, PRG RAM, and the mapper registers. At the moment, we're going to assign all of that to the ROM. But potentially we might need to separate that up later into some of the handles if the cartridge has got RAM, which I don't think this, well maybe it does, and mapper registers. Not that I know what mapper registers are, but oh god. Okay. Something I don't want to have to deal with. 0x FFF. Right. Let's keep going. No rest for the wicked. Alright, if length of bytes is greater than 1. Length of bytes, length of value. There's an exception. Alright, what is values? Value. What is value? Value is an int. Value is an int? Interesting. Where am I getting called by? Address. Oh yeah, now we're bit shifting. So address with that shifted and address with that shifted. Right, so that's going to flip your endianness. That will fix your endianness, yes. Alternatively, sorry, you may sometimes have 3-bit bytes, but again, that could just be fixed by doing some bit shifting and flipping and stuff like you've done there. So I mean, if we're reading it in, we get the reason I've done it this way is that we get it in bytes, which is this kind of weird thing that I don't fully understand yet of why it's structured this way. So I don't believe that you can. Let's do some tests. Can you do bitwise operations? Because I don't believe that you can do a bitwise operation on a hex value. You cannot. Can you do a bitwise operation with 0x00ff like you've suggested? No, so you'd have to do a bitwise operation with another bytes object. Yeah, basically what I want to do is take it out of this bytes format as soon as possible, I think. Because it just makes my life a lot more complicated. The only reason I really need bytes is I want to be able to identify these things, but then when I pull the data out, I think I really want to be converting everything into ints pretty much straight away, with the exception of when I need to work with endianness. I kind of want to do this, which is you can do create an int from the bytes and with the byte order flip to little endian. And I really want to be storing, I don't want to mess around with bytes too much. I think that's going to be a real pain later on. So I'm going to change that now. The reality is once I get it into int form, then not only can I talk directly to it by being like 0xff plus my int, and so I can work in hex or binary, but I can also do those kind of bit shifting things when I need to. Yeah, great points. I think the answer is going to be, let's just do it with ints. So potentially this is just going to be, instead of doing it here, I'll probably have something that, some kind of mix in that collects the data and automatically converts it to an int and passes it through and stuff like that. And then this instruction can decide what to do. Instead of getting the bytes, it'll just get the data in integer form. And it decides what to do with that, with the endianness already dealt with. So let's find all our bytes and let's get rid of them, because I don't like them. The only exception is this ROM thing, because the ROM actually does read bytes and returns bytes. Which is going to be difficult to deal with. And we want it to return bytes. Alright, well, let's change the other things. Let's change this memory owner mix in, because I think that this is going to be the core of it, and then the ROM could just implement a different memory owner. It can contain like a byte memory owner mix in or something. So I'm just going to do this, and let's see what we get. Rename. Do you reckon there's a refactor to do with the typing? That'd be cool. Change signature. Nah. What if I did refactor this? Is this going to rename bytes? Okay. We probably don't want to do that. So let's say that memory is now going to be a list of ints. And we're going to have a get. We're just going to call this get. And we're just going to call this set. And we're going to make this return an int. And we're going to make this be an int. We don't need to do that anyway. Gets int sets int. Right, so that memory. Yeah, this could also return multiple ints, couldn't it? I don't actually think we want this. I think we don't want that. We just want to return a single int. Because the only place that we're using that size thing is when you're pulling out multiple bytes from the ROM. And I think the ROM is going to be its own thing. Cool. Right, and we won't give this a set. We will give it a get, and it'll have a size. Size, which is going to be an int equal to 1. God, I hate this new. That looks so bad. Oh well, what you gonna do? Position to position plus size. And this is going to return some bytes. Gets bytes at given position. Could be multiple bytes. But since a bytes can contain multiple bytes, this is what this is actually going to return. It's just going to return a single bytes object. Whew, my brain. Alright. So now these RAM, PPU, self.rom. Do we have a ROM? Self.rom equals none. Okay. I'm going to move this up here. I'm going to make it equal to... Oh, why does ROM equal none? Run ROM. Oh, because we actually load a ROM. Ooh. Okay. Memory owners are going to be the memory owners, and then we're down here in the memory owner. We're going to check if it's the ROM. And then we'll check if it's any of the actual memory owners. So if ROM self.rom. And then this way a ROM is not actually a memory owner, it's its own separate thing that deals in bytes. And everything else can deal in ints. Yeah, that's awesome. I think that's probably going to be a much nicer solution, and then I just have to worry about casting it when I'm pulling it out. I don't have all these convert statements everywhere, which were looking a bit dodgy. Cool, so ROM looks fine, RAM looks fine, PPU looks fine. Alright, so now we've got to convert these to ints. To do bytes versus ints. Screw that, let's just make them all 0. This is going to be a list of ints. List of int, I suppose. List int. PPU is going to have the same thing. It's going to have 8 registers. Whoa. It's going to be a list of int. List of int. RAM, PPU, ROM. ROM's the same thing. Cool. Alright, I'm glad we're getting there. So the only places I still want to use bytes are using this identifier byte, so I can literally match byte to byte, so I don't have to worry about converting them. This spreg is FD, so I'm just going to make it the same as we did before. It's now an int instead of being a byte, because I feel like that's going to make my life a lot easier. Now I've gotten rid of most of the bytes, right? Where have I still got bytes left? Number of data bytes, fair enough. Data bytes equals get the number of bytes, yep. We're going to pass it to this thing. Instructions have them. That's fair enough. The main has them. The ROM has them. Nice. So we've gotten rid of all our bytes, basically. And now we can do things like bit shifting. Bash a lot simpler because we're dealing with ints, which can be bit shifted. And we can we can now bit shift an int can be bit shifted, and it can also be ANDed with, with that or whatever. All right. So now CPU areg. So what I'm going to have to do here is all these things are now going to have to use, instead of using data bytes 0, low value, that's actually going to return an int, but I actually don't want this function to get anything like, to get any bytes. I want it to get integers. So I'm going to make this non-abstract, and I'm going to rename these so they're not perfect, indeed. I'm sure this will fall apart and we'll have to go back at some point, but I think this makes it a lot easier. So now the data bytes that come in, I want to convert these all to ints, and I want to pass it through to the function. And that's kind of gonna make life a bit easier, I think. So int from bytes, yeah. So I think typically the data bytes that are going to come in, they're not actually always going to be one piece of data. Keep at it. I'm heading to bed. Thank you, Nico. Yeah, it's what time is it? 3:18 p.m. here at the moment. So I'm in random middle of the day, but thanks for watching. Because I think it's, midnight-ish in the US at the moment. Alright, let me try and get my head into the game. Sometimes I believe we will have, thank you for watching, Nick. We will have, different stuff going on. So this LDA is going to take one value out, whereas the store A, absolute, is going to have two values that represent the absolute, and they're going to be in little endian. Whereas store A, abs, and then x, is going to be two values for absolute, and then x for an offset being a separate thing. So we're not always going to be combining the three values into one int. Sometimes some of them will be combined and so on. So I think what we want to do here is to create some mix-ins that are going to tell us the different, not only the different types of indexing, but the different ways that we can access data. And actually, the only way the data is really used is through indexing, right? I think. Oh. So if I think about it, instead of doing this, maybe what we should do is finally get around to doing some addressing. Cool. I think at this point, I'm going to try, I might not go down that road. I might wrap this up. I might make this a bit nicer. And then I might finish for today, because I get the feeling I'm going to get to the point where my brain is going to start failing a bit. And we've made some pretty good progress. So let's do that. Let's not worry about addressing modes today and making them smart. Let's take this back. And let's say to do. Turn this into the correct format. So really what we want it to do is to take in some bytes, and then depending what kind of data it needs out of it, which is typically depends on your addressing mode, to figure out which of those bytes to pull out and which order to pull them out in, and whether they're in little endian, and how to convert them to int. And then basically, based on the instruction type that you have specified, you will get different parameters in. So an STA that is an absolute index will also get the same parameters in as an STY that is absolutely indexed, because they'll both inherit from the absolute indexing mix in. And that way we don't have to worry about dealing with bytes. We just get ints in, which are our values, and we can just directly work with them into the correct int format. But I think at the moment, let's get rid of any exceptions. And I might leave it there. None type does not support any get memory. Is an abstract method. Alright, let's find usages. Alright. What is our memory owner? So the PPU. So the PPU doesn't define a get memory. Super.get memory. No PPU. Return your own memory. Does the RAM do that as well? No. Cool. Bug fixed. Bug not fixed. Self.get memory. What does that return? Position is 8192. So why is the PPU getting things that are routed to 8192? Because it should be. So when we're accessing the memory, we're going to need to offset by our memory start location. All right. So when we do a get, we will say, right, so when we're dealing with actual values that are coming in, memory locations that are coming in from the RAM, we're going to need to be dealing with offset position. So this get is going to need to be position minus self dot memory start location. Why is that erroring? Is that not something that I have? Position, that's an int. Why is this complaining? I don't know. Alright, let's try that. Cool. Instruction not found. That's perfect, because we've run all our other instructions. So if we look at our memory now, if we look at our PPU memory, it's get memory. We have set the first register of the PPU to 16. So we are actually modifying the memory of the PPU. And all through this memory owner, it probably wants me to check that this is going to be a valid position or something. Oh, here we go. Expected type number, got memory mix in, none. Right, cool. Type checking. I should check that that's not out of bounds, but whatever. Expected number, got int. Is number a thing? No, I don't know. Alright, it works. So we have a successful PPU now. Well, we have successful PPU. We have a successful memory model that allows us to set memory values on our PPU, among other things. Cool. I think I'm going to stop there. Does anyone have any questions or thoughts or whatever? And while I'm kind of going to start wrapping this up and committing it and, you know, all that kind of fun stuff. Let's presume that all the changes we made were in our best interest, and let's commit them all. That's definitely a valid assumption. I'll just give it a quick scan. So what have we done today? A lot of things, jeez. So we've implemented status, which is register. So originally this was implemented as a using bitwise shifts and stuff like that. And then it was very kindly pointed out to me that that was probably not a great idea by who pointed that out? The real Jagliano, I believe. Yeah, the real Jagliano pointed that out. So yeah, we've now implemented the status register, and you can see the description here as just a set of things instead of representing it in as a set of memory. The ROM is now has its memory start location and its end location. Everything that it returns is now bytes. So the ROM is now the only thing that still deals in bytes. And it it now can read and give you a number of bytes. We may need to make it have this offset and have everything deal with deal with these offsets, because if things want to reference parts of the ROM, which they probably will, then we'll need to do that. We have RAM now, so we have something where we are storing 2 kilobytes of things, 2 kilobytes worth of data. So 2048 bytes, although we're actually representing them as ints now. We've gotten rid of the bytes. Thank you, Besh. It does look like a fun project. Yeah, we'll see how it goes. I feel like it's going well. This is my second time working on this today, so working on this project, sorry, not today. So it's all been started from scratch, so we'll see how it goes. We now have a PPU that is storing some memory where it will keep its registers. Again, this is probably something where we'll overwrite this memory owner mix-in functionality. So instead of physically storing the data like it is now, but we could say that it's physically storing the data. It'll not only physically store the data, but it'll maintain its own internal status of the registers, much like this class. So instead of having to dereference the hard, what's actually in the memory and do bit shifts to figure out what the status is, we're going to, have our own management of that. We have a memory owner mix-in, which is going to basically it just defines what things we need for a memory owner to have, which is the RAM or the PPU or other things that I'm sure we're going to come across later. Anything that can have access to memory, and it just helps us genericize how we access that, set that, the offsets that are needed for where your address is and all that kind of stuff. So RAM, PPU, CPU. We implemented a couple more instructions. In fact, we implemented all these instructions today. Before this, they didn't actually do anything. Now we have 4 instructions that actually do things. That's pretty cool. They all seem to work. They might operate in a different way. I'm definitely going to work next on getting the addressing modes and stuff in, so I can read in data in a smarter way and not get in bytes, but get in the parameters. and yeah, working on getting more of those instructions in. The CPU is coming along well. It now keeps track of all the registers. It sets them to the correct startup values, and it associates the correct memory location to the correct memory owner, so you know who to pass it to or who to get your data from when you have a memory location. Yeah, that's pretty much it. Alright. Working instructions, RAM, PPU, and status flags. Working instructions started. Cool. Alright, I will push that up now. Yep. Alright, I'm just gonna do that somewhere else. And yeah, thank you very much for coming along and watching. This was a pretty crazy one today. We got a heap of shit done. Started off with no instructions that worked and no RAM, no status flags, no setting anything, and that's all been done, so it's been really good. I'll probably take a break from streaming for a while. I'll probably come back either in a couple of days or next week. I would say probably at a similar time zone to this, so probably starting at around 2 p.m. GST, around that time. Maybe happy to vary it or whatever, we'll see how it goes. Anyway, thank you very much for coming along. Thank you particularly for the people who kind of had some really helpful stuff in chat, helping me make sense of all the things that I'm doing. Happy Bands, The Real Jagliano, Besh, Jay, I'll need to figure this one out, Jay Sudlow, and Nico for being positive. Yeah, it was really fun. So I will, yeah, I will figure out when I'm next going to stream. I'll push all this up. The YouTube video will be available in a couple of hours, I guess, once it finishes uploading. And then when it's done that, I need to cut it down, so I cut out the intro at the start. But yeah, it'll all be available, and I'll push the code up soon. And yeah, thanks for coming along.